Look underneath a moving locomotive and you'll notice something that seems almost wrong. Slung low between the wheels, hanging beneath the frame like an afterthought, is a steel tank the size of a small room. It holds thousands of gallons of diesel fuel, and it sits about as close to the ground as anything on the machine can get. The question worth asking is simple: why there? There's a version of this answer that sounds reasonable but doesn't hold up. People assume the tank sits low for easy refueling access, or because there was nowhere else to put it, or simply because that's how it's always been done. The real answer runs deeper than any of those. The placement of a locomotive's fuel tank reflects a specific set of engineering decisions shaped by physics, federal regulation, decades of accident data, and the particular demands of moving thousands of tons of freight across steel rails at speed. Understanding why the tank sits where it does means understanding how locomotives work, what happens when they don't, and why the engineers who designed these machines made the trade-offs that they did. A modern diesel locomotive isn't powered the way most people imagine. The diesel engine inside doesn't connect mechanically to the wheels. Instead, it drives a generator, which produces electricity, which powers electric traction motors mounted directly on the axles. The diesel engine's only job is making electricity. The wheel's only job is using it. This separation of power generation and power delivery is what makes diesel-electric locomotives so effective at pulling enormous loads from a standing start where the demand on the drivetrain is highest. Feeding that diesel engine requires a significant amount of fuel. A modern unit like the GE AC 4400 CW or EMD SD70 series carries roughly 5,000 gallons in its main tank. At about 7 pounds per gallon, that's 35,000 pounds of fuel sitting on the locomotive before it moves a single mile. Additional tanks hold coolant and lubricating oil. The numbers add up quickly, and where that weight sits matters enormously. The tank itself is a heavy steel structure suspended from the locomotive's underframe, the main structural backbone running the length of the machine. It hangs between the two trucks, the wheeled assemblies that carry the locomotive's weight on the rails. Inside, baffles divide the tank into compartments to prevent fuel from sloshing violently during acceleration or braking. Safety valves can cut off fuel flow if a line ruptures. Grounding cables eliminate static charge buildup. Refueling happens through ports on the side or top, at yards, from trucks or fixed facilities. The locomotive never takes on fuel while moving. The engineering in a fuel system this size is more sophisticated than the tank's plain exterior suggests. Every component exists because something once went wrong without it, and the current design is the accumulated answer to decades of operational experience. That history becomes important when the question turns to why the tank sits where it does, rather than somewhere more obvious. If you want more deep dives into the engineering decisions hiding in plain sight on the machines around you, hitting that like button and subscribing keeps them coming. The low fuel tank didn't appear with modern locomotives. Its logic is older than diesel traction entirely, rooted in the steam era and the physics that govern those machines the same way they govern everything that runs on rails. Steam locomotives came in two broad configurations. Tender types carried water and coal in a separate car coupled behind the engine. Tank types carried everything on board, and the most practical of these used what engineers called a well tank, a water reservoir built low in the frame between the wheels, as close to the ground as the structure allowed. The reason was stability. Water weighs roughly 8 pounds per gallon. Put enough of it high on a locomotive and the machine becomes top-heavy, less stable in curves, more susceptible to rolling forces on uneven track. Drop that same weight into a well beneath the frame and the locomotive plants itself more firmly on the rails. Early diesel designers inherited this logic directly. The first diesel locomotives were built by engineers who'd spent careers on steam, and the instinct to place heavy masses low carried forward without needing to be argued from scratch. What changed over the following decades was the regulatory framework. Through the 1990s and into the 2000s, the Federal Railroad Administration and the Association of American Railroads developed formal crashworthiness standards informed by actual accident investigations. Fuel spills, fires, derailments, and grade crossing collisions all contributed data. The low tank placement that had started as inherited instinct became codified engineering requirement, refined by evidence and tested against specific failure scenarios. The transition from intuition to regulation is the story of most safety engineering. Someone notices a pattern in how things fail. That pattern gets studied. The study produces a standard. The standard gets written into law, and what you see on a locomotive today is the end product of that process, applied to a machine carrying 35,000 pounds of flammable liquid at speed through populated areas. Center of gravity is the concept that explains more about locomotive design than almost anything else, and it's worth spending time with before moving on to regulations and crash tests. Every object has a center of gravity, the single point where its entire weight can be considered to act. For a locomotive, that point sits somewhere in the middle of the machine, higher or lower depending on how the weight's distributed. A high center of gravity makes a vehicle prone to tipping. A low one makes it more stable. The relationship between center of gravity height and track width determines how much lateral force a vehicle can withstand before rolling over. Trains run on a very narrow effective width relative to their height. Steel wheels on steel rails sit on a track gauge of 4 feet, 8.5 inches in North America. The locomotive body rises well above that. The ratio of height to width is less favorable than a car on a paved road, which means center of gravity management matters more, not less, for a machine running on rails. Now add the fuel numbers. 5,000 gallons of diesel, 35,000 pounds mounted as low as the frame allows. If that same weight were mounted on the roof or high in the nose, it would raise the center of gravity significantly on a machine that already carries a massive diesel engine, a large alternator, cooling systems, and electronics stacked inside the car body. The effect on stability and curves would be measurable and negative. On super elevated track where the outer rail is raised to help trains navigate curves, a high center of gravity creates forces that push harder against the outer rail and increase the risk of rollover and any deviation from normal conditions. The low tank doesn't just improve stability under normal operation, it also changes what happens when things start to go wrong. A minor derailment on a locomotive with a low center of gravity behaves differently than the same event on a higher CG machine. The forces involved are lower, the tendency to tip is reduced, the margin between a manageable incident and a catastrophic rollover is wider. Engineers design for normal operation, but the physics of center of gravity work the same way in abnormal situations, and that margin matters when the unexpected happens. Weight distribution across the axles is the other half of this equation. Locomotive traction depends on how firmly the drive wheels press against the rail. Too much weight on one axle and the axle sees excessive wear. Too little and it loses grip. The fuel tank's position between the track allows its weight to distribute relatively evenly across the wheelbase. As fuel burns off during a run, the tank lightens, but because it's centered and low, the shift in center of gravity is minimal compared to what a higher offset tank would produce. Open the hood of a locomotive and the available space inside the car body disappears faster than expected. The diesel engine alone occupies a significant portion of the interior. The main alternator sits directly coupled to it. Cooling systems, including large radiators and fans, take up the long hood sections of most modern units. Electronics fill cabinet after cabinet. Cab sits at one end, configured to meet crew safety requirements. Maintenance across corridors run alongside the engine so technicians can reach components without disassembling half the machine. There is no room inside this arrangement for a 5,000-gallon fuel tank. Even if the volume could be fitted somehow, adding that height and width to the car body would push the locomotive against clearance plate limits, the standard dimensions that determine whether a piece of equipment can safely pass through tunnels, under bridges, and alongside station platforms across the national rail network. The underframe doesn't present these problems. The space below the mainframe rails, between the trucks, exists as functional real estate that no other component can use. The tank fills it without adding height, width, or interference with anything above. The frame itself provides more than just attachment points. The main longitudinal rails of the underframe run along both sides of the tank. In many locomotive designs, the bottom of the frame and additional reinforcing structure partially surround the tank, creating a cradle that absorbs forces that would otherwise act directly on the tank walls. Rocks and debris thrown up by the wheels pass below or around the tank rather than striking it directly. The frame geometry channels energy around the fuel system during the kinds of impacts that occur in normal operations, switches, rough track, and minor collisions with objects on the line. This structural protection isn't complete. The tank remains exposed at the bottom and sides to impacts of sufficient force. Addressing that vulnerability is partly what the federal regulatory standards exist to do, setting requirements for how much the tank and its attachments must withstand before allowing any breach. The Federal Railroad Administration's crashworthiness standards for locomotives aren't abstract guidelines. They specify force values that tank structures must survive intact, and those numbers come from real accident data rather than theoretical modeling alone. Under 49 CFR Part 238 and the AAR's S5506 standard, fuel tanks must withstand a set of defined load scenarios without rupturing. A minor derailment scenario requires the tank to support a portion of the locomotive's weight bearing directly on the rail, the condition that occurs when a derailed locomotive slides along the track surface. The jackknife scenario applies extreme compressive loads along the locomotive's length, replicating what happens when coupled cars compress violently in an emergency stop or collision. The side impact scenario applies a specified force representing an 80,000-pound truck striking the locomotive at a grade crossing with approximately 200,000 pounds of equivalent impact force. These aren't pass-fail tests on paper. The tank structures are physically tested and the results compared against requirements. Modern tanks use thicker steel than their predecessors, improved weld specifications, better attachment hardware, and compartmentalization that limits how much fuel can escape even if one section is compromised. A breach in one compartment can be isolated while the others retain their contents. The placement of the tank under the frame serves the crashworthiness requirements in a specific way. In the side impact scenario, the frame rails above the tank absorb some of the force before it reaches the tank walls. In the derailment scenario, the tank's low position means it contacts the rail surface directly rather than falling from height, reducing the impact energy involved. In the jackknife scenario, the tank's attachment to the main frame structure means it moves with the locomotive rather than separately, which limits the differential forces acting on the connections. Fires following derailments are the outcome the entire system is most concerned with preventing. Diesel fuel is flammable, and a locomotive carries enough of it to sustain a serious fire for a long time. The design approach doesn't try to prevent spills entirely under all conditions. It tries to limit spill volumes, keeping spilled fuel away from ignition sources like the exhaust system and electrical components mounted higher in the locomotive, and to ensure that any fire that does start doesn't have immediate access to the full tank contents. The low placement, the compartmentalization, the placement of the tank away from the hot exhaust stack, and the safety cutoff valves all contribute to this outcome. Rail remains one of the safest modes of transport for large volumes of flammable materials, and the fuel tank design is part of why. The history of how these standards developed matters as much as the standards themselves. They didn't appear fully formed. They grew from accident investigations, from NTSB and FRA reports on specific incidents, from the gradual accumulation of data about how fuel systems behave when things go wrong. Each revision tightened the requirements based on what the previous generation of design had failed to prevent. The logical question after all of this is whether another placement can do the same job better. The answer requires looking at each alternative honestly. Roof or high-mounted tanks would solve exactly none of the problems the current design addresses and create several new ones. Raising 35,000 pounds of fuel to the top of the car body would substantially increase the center of gravity, worsen stability in curves, increase rollover risk in derailments, and place the fuel source adjacent to the cooling and exhaust systems where heat and ignition sources are concentrated. Clearance plate limits would likely be exceeded. The structural requirements for supporting that weight at height would add significant mass to the car body structure itself. A separate fuel tender car, analogous to the coal and water tenders of the steam era, appears occasionally in specialized applications. Some CSX operations have used fuel tender cars on long routes where tank capacity would otherwise require additional stops. The trade-offs are real. A tender adds length to the consist, complicates operations at terminals, creates a coupling between the locomotive and the tender that becomes a potential failure point in accidents and introduces the possibility of separation in a severe collision. For regular operations, the disadvantages outweigh the range benefit that motivates the design in the first place. Internal tanks, fully enclosed within the car body, run immediately into the space problem described earlier. The car body has no room. Reducing the tank to a size that would fit means either reducing range significantly or accepting more frequent refueling stops, which adds operational complexity and cost. Access for inspection and maintenance becomes more difficult when the tank is buried inside the machine rather than accessible from below. Battery electric and hydrogen fuel cell locomotives are under development and testing, and they approach the question from a different direction entirely, eliminating the diesel tank in favor of energy storage systems with their own placement considerations. For now, diesel electric remains the standard for heavy freight operations because no alternative matches its energy density, range, and power output for the workloads involved. The case for the underframe tank isn't theoretical. It's supported by decades of accident investigation data and crash testing that produce the regulatory standards currently in place. FRA crash simulations, including physical testing of tank structures under defined load scenarios, have validated the current design approach. Modern tanks consistently meet or exceed the specified loads without rupture and controlled testing. The improvements implemented after the 1990s studies, thicker steel, better welds, improved baffles, more robust attachment hardware, reduce the incidence and severity of fuel spills and real derailments compared to earlier designs. The statistical record supports the design. Fuel spills and locomotive accidents do occur, but catastrophic fires are uncommon. When fires do start, the compartmentalization and safety valve systems limit how much fuel feeds them. In comparison to alternative modes of transporting equivalent volumes of flammable material consistently favors rail. The fuel tank placement is one component of that outcome, but a meaningful one. Every part of a working locomotive is there because someone decided it should be, because experience showed it worked better that way, or because a regulation written after an accident required it. The fuel tank hanging beneath the frame looks like an exposed afterthought. It's actually quite the opposite. A carefully positioned mass whose location was chosen for stability, refined for crashworthiness, tested against specific failure scenarios, and optimized for the operational realities of machines that run millions of miles hauling freight across a continent. The low center of gravity that placement creates makes the locomotive more stable in curves, better behaved on imperfect track, and more forgiving when the unexpected happens. The structural protection the frame provides reduces the forces that reach the tank in the most common accident scenarios. The regulatory framework that governs the tank's design and attachment reflects what engineers learned from studying the consequences when earlier designs weren't good enough. So, next time a locomotive passes you by, the tank hanging below the frame isn't an oversight. It's one of the most deliberate decisions on the machine. That's what good engineering looks like from the outside: unremarkable, functional, and exactly where it needs to be. If this kind of deep dive into the engineering decisions hiding inside everyday machines interests you, do us a favor, because hitting that like button and subscribing is the easiest way to make sure you don't miss the next one.